Okay, good morning. Today the plan is to continue with the model formulation of the GLM, first in the abstract terms that we started last time, and then specifically with respect to probabilistic aspects. And once we have basically introduced this here, so this equation, so the model formulation for the GLM in abstract terms, then we look at how this looks if we're talking about fMRI data analysis, because it doesn't really make much sense, as you saw when I first showed you what an fMRI data analysis is, to just show you that for fMRI without explaining the abstract background. But once we have that, we can, of course, look at it again, and we should. So again, the general topic currently is model formulation for the GLM. So we're just formulating a model. We are not talking about estimating any parameters of this model yet. We are not talking about doing some form of model evaluation or deriving p-values. All of this will come, but right now we're just formulating the model. And last time we first discussed some aspects of experimental design, with essentially the only important distinction for what we are interested in being the distinction between the independent and the dependent experimental variable. So somebody just repeat what the difference is. So what's the dependent, what's the independent variable in experimental design? Forgot it.
The independent is the outcome of our measurement, and the independent parameters being set for the design.
Yeah. So I'm actually not too keen on these specific terms, and of course you also know that these terms are somewhat counterintuitive, because the dependent variable is something that you basically have not much influence on, and the independent variable is where you have the influence on. The important thing is that you distinguish that you measure something, and this is the outcome. It's called the dependent variable in psychology, statistics, and you also manipulate something of the experimental design, and this is called the independent variable. So this is what we discussed, and then we discussed the basic multiple linear regression form of the GLM. So that's this, what we have at 2 here, where I is the number of data points, and we're looking at a single data point here. So can somebody briefly explain what these yi, xi1, beta1, and so on are? Now, with respect, of course, to the variables, experimental variables that we just heard. So what is yi? We just go on there.
Just one data point.
And in terms of these independent, dependent variables?
That's the dependent.
Exactly. So this is what you measure. And for fMRI, what would yi be? We mentioned it. We haven't really discussed it in detail, but.
I know I read it, but I can't remember.
Okay. So for fMRI, it would just be the MR signal at a given time point of the experiment in one voxel, so just a number. Okay, so the xi1, xi2, and so on, what are they? And what could that be, for example? Yeah, let's keep it at that. We will go into more detail how these xi1 and so on are created for fMRI, but go on with the betas. So what are these beta 1, beta 2?
That's the weight dividend. So,
and where does it come from, this weight? It's a little bit of a tricky question.
That's how much the independent variable
That's true, and we will see later where they are coming from. So the general idea is that these are, of course, parameters and or effect sizes, and they are given by nature. So with doing the experiment, we try to measure them, and what we need to do, because nature fixes them, but we don't know them, we need to estimate them. And so on the one hand, during model formulation, we assume that these weights are there and they are fixed by nature. And once we get to model estimation, we will see that we estimate them. So in this sense, it was a little bit of a trick question because it's different from what you have seen before, where you just compute averages and so on. So these are parameters that are, as we will discuss later on, true but unknown parameters, but we will get to that. For now, just assume that you know them, however, in whichever way this might have happened. Okay, so that was this, so we discussed that, and then we basically summarize this over data points and introduce the matrix formulation for this deterministic aspect of the GLM. So this is what I mean here with this y equals x beta. And we looked at an example, namely simple linear regression. So does anyone remember what now in 3 here, y, x, and beta mean? And maybe even specifically in the case of a simple linear regression design? So I'm talking about this, and there's a y, there's an x, and a beta. And we also specifically discussed this y being equal to x and beta for simple linear regression. So what is y, what is x, and what's beta?
Not an experimental thing.
But mathematically.
Better is the slope.
Yeah, in simple linear regression, but more generally. So what is y in general when we talk about the model formulation of the GLM? No. It's not really a matrix, or let's say it's a very special matrix. Yeah. So how many entries does this vector have?
One per, and so it's one column that goes depending on
how many? Yeah. How many?
Yeah,
what?
Data points.
Data points, exactly. So y is a vector, as you say. It's a list of numbers, and it has as many entries as there are data points, and n is the number of data points. So then in this setting, what is x? Not only talking about simple linear regression, but
it's a metric,
yeah.
so n times n.
N times, yeah, m, but actually we call the number of parameters.
Right, from the better vector.
Yeah, and we call the number of parameters p. It's just a convention. It doesn't matter. I mean, that's really detailed, but we will use this convention all the time, so it helps to get used to it. And what is better then?
The vector, p entries.
Yeah, exactly. So that is kind of the data vector, the design matrix, and the parameter vector. And now for simple linear regression, how does the design matrix look? That was also what we discussed last time. So somebody from this side here. Do you remember how the design matrix looks for simple linear regression designs?
Just 2 columns, and the first one was just a vector of ones, and basically 1 column of x's. That would be like x1, 2.
Which are the values, of course, of the independent variable. Exactly. And then if you have this ordering of a vector of ones or column of ones and a column of the values of the independent variable, what is the interpretation of the corresponding beta parameters? Well, it's actually understandable. So you just defined a design matrix with a column of ones and a column of x's, right? And in this formula, you multiply this design matrix with a beta vector, which of course needs to have 2 entries because there are 2 columns of the design matrix. That means the beta parameter has 2 entries. And the question is, what is the interpretation or what is the meaning of the first and the second beta parameter in this beta vector? If you think about simple linear regression.
They side on like the waves of the axis.
Yeah, and if you relate this to what you have learned about simple linear regression before, where there's always something like a slope and an offset. Yeah, so it's so you really need to think in detail about this and also remember these things. So you did well, but it's also important that you really zoom in. So anyone else?
Vector 1 should be the intercept and 2 the slope.
Yeah. So this is, if you think again about the simple linear regression, if you plot this, then you have always a straight line in terms of the model prediction. And because these ones get multiplied with the first parameter and added to the whole thing, they always add for each data point, so they can be interpreted as the offset, and the second beta then multiplies each independent variable and forms the slope. So yeah, so these are the kind of things, I mean, of course they are in the script, but these are the things that are also important to basically learn. Yeah, good. But that was all right. So we have basically last time discussed the deterministic aspects of this model. And because we are dealing with probabilistic models or statistical models if you want, we of course also need to talk about the probabilistic or stochastic components, and this is what we want to do then next. So the first thing that I would like to talk about is the general idea of having Gaussian errors or Gaussian noise in these general linear models. Then the important thing of IID samples or IID noise. That's the number 5, and then finally, yeah, the interpretation and the full understanding of this model formulation that you also see here. So that's of course what this whole first section is about. Good. Are there any questions left before we proceed from last time? Sorry. Anything that you would like to clarify or talk about? No. Good. Then let's talk about the additive Gaussian noise, and let's basically follow in the script with this part on the Gaussian assumption. So although we just talked about it, let's briefly revise what we've seen so far. So what we want to clarify is what this thing that I'm just writing down here means and how it's useful and so on, but mainly what it means. And what we've seen so far is, as we just heard, is that the y corresponds to an n-dimensional data vector. So this models data that we observe, and it models for a given observation a single data point. Yeah? So it's a univariate model. Then we have a design matrix which encodes information about the independent variable or variables, and we have our beta parameter vector which and has the information about how much each independent variable contributes to the data. And this can either be as it is in nature, or we later on we will estimate it, but we will make the distinction clearer later on. For the moment we assume it's given and we just know the beta weights. Now, if we write this out again, what is behind this and what you should always see when you see this equation is, of course, a vector of data points where each of these yi is just a real number. So something like 10.2 or 210.34, something like this. Then the x is, of course, the design matrix. And here you should, of course, also always, oops, wrong way around. you should also see this behind this up to the pth column. And then we have the beta parameter vector. Let's do this beta 1, beta 2, 2, beta p. And this is what we discussed last time. And this is purely deterministic, so there's nothing like a random variable in there, especially not in the classical setting, in the Bayesian setting. Actually, this would be a random variable, but we are dealing with the classical setting. So there are so far no random variables involved. But then what we have in addition in this equation of the GLM, we have this epsilon here. And so the full equation, which we didn't discuss last time because we only focus on the deterministic aspect, is actually plus this epsilon. Now the question is what this epsilon is. And the first thing that you should realize in this kind of setting is that if we have here an n-dimensional vector and we add something to it, so think again what we have here. So we have a, let's make this clear, we have here something that is n-dimensional. If we multiply the design matrix and the beta parameter vector, what do we get? In terms of a vector or matrix or something? Mu? And what? Yeah, what's the size of this mu? Think again about how matrix multiplication works. So here you have something that's So what you have here is a matrix product between an n times p matrix and a p times 1 matrix or vector, and this is of course well defined in the sense that these are the inner dimensions are the same, so you can actually compute this, and then the outcome is always given by the outer dimensions, so it's something that is n times 1, as you said, and as you have said also we call this mu for reasons that will become clear. So that's this and this together. Now, if you have this here, so you have an n-dimensional vector being equal to an n-dimensional vector plus some epsilon. What does epsilon need to be? If you think about the rules of matrix addition.
A vector of the same size. A vector of the same size.
A vector of the same size, and the size would be
n.
Yeah. So epsilon is definitely a vector of size n. Yeah. So we can also rewrite this as epsilon 1, epsilon 2, epsilon n. Yeah. So that's the first thing to realize, that this epsilon here is a vector. It's actually a kind of a special vector because it's, as we will see in a second, can either view it as a random vector or you can view it as the realization of a random vector. Then it's really a vector. So if you view it as a realization, then it's really an n-dimensional real vector. If you view it as a random vector, then it's a random vector and can take on different values. So what is it about? What's going on? So to think about that, we can first look again at one specific row of this whole thing. So let's say we're looking again at a yi. Then of course, like previously, this yi is now given by our xi1 times beta 1 plus xi2 beta 2 and so on, xi p beta p, and now we have this extra thing plus epsilon I, yeah, so the ith entry in this. So we now have here our deterministic component, This is what we discussed last time. And the epsilon here is a random component or stochastic or probabilistic term. So in the script I call this a probabilistic term. You can also call it a random term. Now we can also, of course, write this. This really doesn't matter much, but it looks a little bit simpler. By calling this deterministic term just mu I, because it's just one number, and then we don't have to write always this xi1, beta 1, and so on. So just again to make clear what these symbols mean, if this is, for example, fmi, then this would be something like 210, 37. This would be something like, let's, for example, the numbers of course now don't matter, but just that you are aware that these symbols, they are not just abstract math symbols that may mean this or that. They just mean numbers, and it's just an equation that says what you have on the left side here, 210.37 is given by mu I 209 plus epsilon I here 137. Then it's an equation, and it's fine. Now the mu I we know how to compute, because if we fix the design matrix and we fix the parameters, then we get the mu I. Now the epsilon I is different in the sense that we don't specify in model formulation epsilon I explicitly. We don't say it's this and that number that you can compute by this and that, but it's conceived as the realization of a Gaussian random variable. So this is something that we write like this: epsilon I is normally distributed, and it's actually normally distributed with expectation parameter 0 and with a variance parameter that we call sigma square. Good. So who remembers the probability density function of a Gaussian random variable? Something that we would write like this. So what's the formula here for this probability density function from the mathematical preliminaries?
1 divided by 2 sigma squared in 2p sigma squared in square root. And then the exponential function of 1 minus 1 divided by 2 sigma squared, and then x minus the middle, how do you say it? Then the whole thing squared.
Yeah, exactly. Very good. So that's the probability density function of a Gaussian random variable. If you plot this, of course, you get something that you have seen many times. So I think all messy. All psychologists will have seen something like this. So this is now here our probability density function, nx mu sigma squared, and this is of course here x going from essentially minus infinity to plus infinity, or just being in the real numbers. Now the mu and the sigma square, what do they tell us about the form of this curve that we see here? So what does mu say and what does sigma square say? Now someone else, but also someone else. Some psychologists, you've done this a lot. So if you think back about the Gaussians in undergrad statistics, you discuss Gaussians. Don't tell me you didn't discuss Gaussians. And they had parameters. And the question is what these parameters are now, the mu and the sigma square. So what do they mean intuitively? What do they parameterize? But did you see a Gaussian?
No.
Did you do a Z-test or T-test?
Yeah.
Yeah, and you didn't see a Gaussian?
I don't recall.
Because that's weird, but this has to do with how undergraduate statistics is taught. Yeah.
It's just like statistics for social sciences, maybe. I don't know. I just don't recall right now.
No. Anyone? Okay, then anyone else who remembers what mu and sigma squares, so the parameters of a Gaussian mean?
There's expectation where also supposition.
Exactly.
And the other one is the variance, how big, how large is the curve is.
Exactly. So the width of this is specified by sigma square, and the location of this is specified by mu. So for example, if you have a different setting for mu and sigma square, you can have, for example, something like this. So this would now have its mu, so its location here, and as you see, the width of this Gaussian is, or this probability density function of a Gaussian is much smaller. It's actually not up to scale because it needs to be normalized over the entire real numbers. So actually, this peak here would have to be much larger. But yeah, you get the idea. So the mu is what I always call the expectation parameter. And sigma square is what I call the variance parameter. So from the mathematical preliminaries, you will know that expectations and variances are something that you can compute on any random variable. And it turns out that for the Gaussian, the expectation corresponds to mu and the variance corresponds to sigma square. And to distinguish between calling this the expectation, where you would basically compute something on a random variable, I call these expectation parameter and variance parameter. These are also often called mean and variance. One can do that, it's fine, it's very conventional, but it doesn't really make clear that these are parameters of a probability density function which describes a distribution, so that's why I prefer this nomenclature. Good. Now, what we have already said is that we have this epsilon I is supposed to be distributed according to a Gaussian, a univariate Gaussian or normal distribution. So Gaussian and normal, that's the same thing. I tend to say Gaussian more often. And this Gaussian, this univariate Gaussian, is supposed to have an expectation parameter of 0, so it's the highest density is at 0, and it has a variance of sigma square. So let's think about what that means. So what we now are interested in is this. So again, we just have a Gaussian. A Gaussian which is now located at 0. Doesn't get nicer. It's located at 0. So now from your intuition about, and it's about epsilon or epsilon I, from your intuition about probability distributions, if you now would take a sample from this distribution, or let's phrase this in the other way. If you, let's say I sample something, let's do it like this. So this is -1, this is 1, this is 2. If you take a sample from this distribution, what is a likely value that you will observe? Yeah. But maybe a little bit more specifically for this. Yeah. how likely is it that you observe exactly 0?
But not that it's like around this point.
Exactly. So that's the point here. So you are likely, when you sample from this, to observe values that are around 0 here. So something like -0.1, -0.05, -0.005, for example, plus 1.02, values like this. And you will observe these values around here quite often. Will you ever observe something like minus 1.5? Yeah, but not that often, obviously. And the same thing here. So if you think about taking samples from this Gaussian, what you should think is that if you take repeated samples from this, you will obtain something like this. Let's say you take a first sample, epsilon1, you get, let's say, this. And then you take a sample again, and you get this. And then you take a sample again, and you get this. You take a sample again, you get this. Then you get a sample again, and you get this. So it's a little bit out, it's actually quite far out, but sometimes it happens. Then you take samples again, and you get again values that center around the expectation of this Gaussian, and the expectation of this Gaussian is obviously 0. Yeah, so that's the intuition you should have when I say, okay, these values are distributed according to a Gaussian distribution with expectation parameter 0. And of course, the variance parameter determines how likely it is that you observe kind of extreme values. So again, if you have a different a second Gaussian here that has a much smaller variance, or something like this, then it's of course much more unlikely that you observe values that, for example, are larger than 1 or smaller than -1. Yeah, it still happened. There's still a positive probability density associated with them, but it's very unlikely. Yeah, so most of the values that you will observe will then be much closer to 0. And essentially, this is the idea about this epsilon I. So for the ith data point, epsilon I is conceived as a random sample from a Gaussian distribution centered on 0. So let's maybe look at an example again. So to drive this point home, so if we have, for example, 3 data points, y1, y2, y3, and now we evaluated the product of the design matrix and the beta parameters to give us our mu1, mu2, mu3. And we're talking about this epsilon1 plus epsilon2 plus epsilon3. Then, for example, what we could have if we, let's make this very concrete, if we have for the design matrix the simple linear regression kind of design matrix, and these beta parameters, what do we get for mu1, mu2, and mu3? So what do we get for mu1, mu2, and mu3? Somebody? You did it last time already, I remember that. Somebody else who didn't do it last time. Somebody who's new to matrix multiplication.
First entry would be 3, so 1 times 1 is 1 times 2, then 5, and 7.
Yeah. Exactly. So these are our mu values. So we can essentially plug them in. So we have y1, y2, y3 now being 3, 5, and 7. And as you've seen, we didn't need to invoke any sampling or any random concepts. We just know x, we know beta, and then we just know mu. It's all deterministic. And now we want to sample our epsilon 1, 2, 3. And we, as I already said, they are. This is a Gaussian. It's centered on 0. So that's our distribution over epsilon I. And now I'm doing the random number generation. So the first sample that I take is here. And then I take another sample for epsilon 2, and this is here. And then I take another sample for epsilon 3, and this is here. So these were now just sampled. And let's say, okay, this in terms of scale, this is 1, and this is -1. So the first epsilon 1 came out as 0.2, I guess. Plus 0.2. The second came out as minus 0.7. And the third came out as -0.1. So if we then evaluate y1, y2, and y3, we get 3.2, 4.3, and 6.9, right? Good. So of course you can also, if you like this more in a more picturesque manner, this is something you can, of course, again, for the simple linear regression, think about the following. So these values that we just created in terms of the mu, they, if we have, you can actually use them. Let's use them and then just put in some more. So we had our independent random, our independent variable, not random, our independent experimental variable, were 1, 2, 3, and we will put in some more, 5, 6. Then our mu values that we computed here were 3, 5, and 7. So let's make this a little bit smaller here on the y. So here with 1, 2, 3, 4, 5, 6, 7, 8. Oh, it's going up quite quickly. So for our independent variable x being 1, we have 3. For 2 we have 5, and for 3 we have 7. So this is our mu1, mu2, mu3. And then of course you can already see, because the offset is 2, as you know, that means that the offset or the intercept is at 2. Does that make sense? Sorry, I'm confused. The offset is 1. Sorry. So this is the slope, and this is the offset. Ich bin ein normaler Mensch. You know that? Good. So this is the slope and this is the offset. The offset is 1, hence at 0 we are here at 1. Of course, this also makes much more sense. So this would be our mu0. And if we go to 4, we can of course also compute this. So that would be 1 plus 4 times 2, that would be 9. So we are getting, and this is of course not surprisingly, we're just getting the straight line here. But remember that these are the mu values, so essentially this whole thing is our mu vector. And then what we just did is that we sampled values around that, and we got a little bit more than 3, a little bit more than 4, so something here, and then a little bit less than 3. And let's assume we sample again. So one way, if you want, it doesn't really make sense, but if you want, you can envision a Gaussian over centered essentially on this, because it's centered on 0, but it always gets at this mu. We will come back to that. So we could also sample here, and then we might end up a little bit above again, and we can also sample here, and we might end up a little bit below again. So these are, it's actually not that nice, actually, as I just realized, because what I've plotted now is already the epsilon plus the mu. To just plot the epsilon, what one would need to do is, actually, that was not that nice. We need to plot them where they really are, right? And where they really are is around 0. So let's plot them where they really are. So we had something here, then we had something also a little bit negative, then positive, sorry. Come on. So we had something positive here, something a little bit negative here, something a little bit negative here. Let's say we have something more positive here, and something negative here. And now, and this is why I'm redoing this, if we now add these epsilons, so this would be our epsilon 4, epsilon 3, epsilon 2, epsilon 1, epsilon 0. If we now add those, then we get our y's, and they are of course the ones that I just previously introduced, so something around here. Here we get a little bit, so mu1 plus epsilon 1 is around here. Mu2 plus epsilon 2 is here. Mu3 plus epsilon 3 is a little bit here, and mu4 plus epsilon is here. So let's write this out. So this is y4 being mu4 plus epsilon 4, and this would be of course our y3, y2, y1 and y0. Yeah, so now I'm just connecting those. So now what this shows, and what I try to make fairly explicit here, is that how the general linear model works as a generative model of data. So on the one hand, you specify a deterministic aspect by fixing the design matrix and the parameters, and what you get from this is the expectation. And for a simple linear regression design, this expectation always just corresponds to a straight line. This is not the case for multiple linear regression designs, ANOVA designs, and whatsoever. The straight line is specific to simple linear regression, but it's a good starting point. So that's what it specifies. Then it specifies that there's an additive error component, or an additive noise component, or however you want to call it. This additive noise component is distributed according to a Gaussian distribution, centered at 0 and with a given variance. If you sample this, as we did here for our epsilons, then you get values that are distributed around 0. And if you add them then to the deterministic aspect, then you get the data point. Yeah, and so we created data points here, y0, y1, y0, y1, and so on, and have sampled data from this model. Yeah, of course you can implement this whole thing in a computer, so you don't need to be your own random number generator. So you can specify any design matrix you're interested in. For example, a simple linear regression design matrix is here. Specify some beta parameters, specify the variance parameter of the noise, and then let the computer evaluate the expectation parameter mu, and also sample the noise or error values epsilon I. Yeah. So this is really crucial here, so that you understand that the general linear model, like any statistical model, can be viewed from a data generating perspective. You fix the parameters, you set them to some values, let's say. You set the design matrix, you set the variance parameter, and then you compute the expectation and sample the errors, and then you have some simulated data. Yeah? Questions about this? No. Good. Then let's have a break and continue at 9 to talk more about the epsilon.